Hello everybody. So this is our rank booster 10. This question was asked in 2025 June NET exam. So let's start. The activation energy and enthalpy change in H2 plus I2 giving to HI are 167 kilojoules per mole and minus 8 kilojoules per moles respectively. So if you can see from here, what they have said is the enthalpy change which is given. Enthalpy change is negative. This is one of the things that we have to note. So if delta H is negative, we understand that this whole process is exothermic, right? So this whole process is exothermic. Now, assuming the pre-exponential factors for the production and the decomposition of HI to be the same at all temperatures, the correct options is, so they have given Kp and Kd, which are the rate constants for the production and decomposition of HI. So they have asked the temperature dependence again, which is something related to Arrhenius equation. So the option says that Kp and Kd have same value, have same temperature dependence. Kd changes more rapidly than Kp. Kp changes more rapidly with temperature than Kd, and the activation energies for the production and the decompositions of HI are the same. Okay, so this is actually not a numerical question. It is a concept-based question. So if the process is exothermic, what can we write? If the process is exothermic, we can understand that these are the positions of the reactants. Let's say it forms a transition state and then it forms the product. Correct. So the energy of the products would be lower than the energy of the reactants. Why? Because it is exothermic. Okay. Now, if you look at the forward reaction where the reactants are becoming the products, you can understand that this is your activation energy. This is your activation energy for the production of HI, let's say. So this is H2 plus I2, and then it forms product HI. So to form HI, for the production of HI, this is the activation energy, EAP. Okay. And if you check the reverse process, from here, I'm using a different color so that you can understand. From here, HI, if it decomposes to H2 and I2, this much will be the activation energy corresponding to the decomposition. Okay, so P stands for production and D stands for decomposition. So it is clearly seen that the activation energy which is required for the decomposition of HI is greater than the activation energy for the production of HI. So of course, option D is not the correct answer because in option D, they have said that the activation energies for the production and the decomposition of HI are the same. It's not the same. The activation energy for the decomposition is higher. Okay. Now there are two ways in which you can solve this problem. One concept is if the activation energy of the decomposition is higher, then the temperature dependence of the rate constant associated with decomposition will be higher. This is one concept that you have to know. All right. So if you see that the activation energy of decomposition is higher, which means the rate constant which is associated with the decomposition is Kd, and that means Kd is associated or will have more temperature dependence or that will change more rapidly than that of Kp. So Kd changes more rapidly than Kp with temperature, and the correct answer is option B. This is one concept that you have to know. Okay. Option B. Okay, I hope that is understood. For example, let's say we have a hypothetical case where this is how the energy profile diagram looks like. Okay, so here if you can see the activation energy for the formation, let's say that is EA1, is greater than the activation energy for the reversible process EA2. So if you can see over here, EA1, this is a different hypothetical case, just for your sake of understanding. EA1 is greater than EA2, and hence the temperature dependence, okay, of K1 will be much dominant, is dominant over K2. I hope you got it. That means if you increase the temperature, K1 will change more rapidly than that of K2 because EA1 is larger than EA2. This is one thing. Now there is another approach as well. So for equilibrium processes, so you have equilibrium process over here where H2 plus I2 is becoming HI, and you have production rate constant and decomposition rate constant. Okay, now generally, when you have K equilibrium, which is Kp by Kd, okay, K equilibrium as a whole increases as the temperature increases if the process is endothermic. And K equilibrium decreases as the temperature increases if the process is exothermic. Very important. Okay. So if you have an endothermic process, as the temperature rises, your overall equilibrium constant increases. But if you have an exothermic process, as the temperature increases, your overall equilibrium constant decreases. So let's take our case. Our case is exothermic, right? Our case is exothermic. So in our case, we have Kp by Kd, and as temperature increases, you have to note this. As temperature increases, okay, both Kp and Kd will increase. So please pay attention. As your temperature increases, individual rate constants will of course increase, because that is something that we have learned from Arrhenius equation. More the temperature, more the number of effective collisions, and more the production of the products, and hence your rate constant increases. Correct. So if I take certain examples, for example, initially, okay, just for the sake of examples, let's say that initially, this Kp, the value of Kp was some random units. Okay, I'm just taking random units, 3. And Kd was, let's say, 2. This was my value. So K equilibrium, this is initially. So K equilibrium will be 3 by 2, which is 1.5. I'm not taking the units, whatever random units they are. Okay. Now, after the temperature increase, after temperature rise, let's say. Now, when you rise and when you increase your temperatures, your Kp will increase, your Kd will also increase. Okay, let's say that your Kp increases. That is natural. As temperature increases, your rate constant will definitely increase. Right. So, after the temperature rise, because it is an endothermic process, sorry, not endothermic. Because it is an exothermic process, your overall K equilibrium should decrease. Okay, so I'm taking another random value. So let's say that your Kp increased from 3 to 5 units. As temperature increases, rate constant increases. And your Kd, also as temperature increases, your Kd value increases, and let's say it has reached 10. Now, what is the equilibrium value? The equilibrium constant is 5 by 10, which is 0.5. So can you see this? I hope you can understand it now. So because this is an endothermic process, after the temperature rise, your equilibrium has fallen down. So that condition is satisfied. If that has to fall down, your temperature dependence on Kd is more than that of Kp, correct? See, the Kp value has increased from 3 to 5, a difference of 2 units only. But your KD value has changed dramatically from 2 to 10. There is a change of 8 units. So even though both of these rate constants will increase with temperature, the effect of the temperature is more dominant on KD. It is more dominant on KD. Okay? And that's how the overall equilibrium constant also falls as the temperature rises because it is exothermic. So if you can see, KD has got a larger dependence on temperature. So KD changes more rapidly than KP with temperature. Option B is the correct answer. Okay, it's a very good question. Make sure that you revise it before your exams. Okay. All right. So thank you.